Okay, so let's begin lecture number 15 on random processes in this course NE402 Intermediate Nuclear Engineering, covering diffusion and transport of radiation and Monte Carlo simulation. The first 14 lectures were on basic introduction to nuclear engineering, neutron diffusion, and neutron transport. I'm now going to come to the third method and the second methodology of this course. The first methodology being deterministic diffusion and transport, and the one that I'm going to come to is a stochastic methodology named the Monte Carlo method. Now, this is a shift we're going to do from deterministic to stochastic way of thinking. So before I come to Monte Carlo method, I think it's very important for you to get a basic grip of some concepts in random processes and some basic probability and statistics, which we are going to use a lot in Monte Carlo simulation. So today's lecture and maybe the next one also. So either we'll have one lecture on this or let's see how it goes today. If I can cover all these things, then it's fine. It will be in one lecture. If I cannot cover, then we'll do half of this now and half of this tomorrow. So what I'm going to look at are random processes. Now, random processes is a very commonly used term across science and engineering and finance because the stock market goes up and down. So it's something that's used a lot. We're very familiar with it in daily life. Then I'll talk a little bit about Markovian processes. Then what do we mean by, in statistics, when you're carrying out a survey, then you have a population and you want to take a small sample from the population, and then you want to collect some data, and then you want to infer. Now, inference is something that you use the sample data for, and you infer on what the population would be thinking. So if you want to know what population of people in a country like red cars, for example. So you cannot go to the 200-300 million people in the country. But what you can do is you can take a sample. Now, Gallup polls and all those kind of polls which you see say that this is what people like and that's what people don't like. So how is that done? So that's done by taking a finite sample. So data collectors can either telephone people or send an email. So, but how good is the conclusion that you draw from a sample, and how good is it on drawing an inference on what the population thinks or says? Then I'll come to random variables. Now these are variables which can represent many values. I'll come to a PDF, a probability distribution function, and an associated CDF, a cumulative distribution function. Then we look at variance, covariance, correlation. These are lots of terms used in statistics. Then random numbers. Random numbers are what WhatsApp even uses to convert the message that you send into something that goes between the sender and the receiver in such a way that nobody can read your message. So the secrecy of your message is ensured by converting it using random numbers into something which cannot be cracked, some code which cannot be cracked. Then sampling, how do you sample from some standard probability distribution functions, PDFs, and how do you sample from some non-analytic PDFs? Then how do you measure distance between two places, just like we measure distance between one end of the room and the other, and we put a tape and we say it's 15 feet long. So when you measure distance, then how do you measure distance when you're talking about PDFs? So that is the Kullback-Leibler Divergence, and that is a metric for PDFs. Okay, then we'll see the law of large numbers, the central limit theorem, Chebyshev's inequality, and what these mean to sampling, because we're going to use all these concepts in Monte Carlo simulation. So these form the basis of the Monte Carlo method. So they're very important, and usually an engineering student would have read this in a full course on probability and statistics. But sometimes when we are reading courses, when you're sitting in those courses as an undergraduate student, as a grad student, then at that point you do not realize how it applies and where it applies. So my way of teaching that would be uh, from an application point of view, that how are we going to use it? Okay, so again, as in all other lectures, this is my name, this is my cell number, this is my personal email, that's my official email, and that's my personal website. And you're welcome to send feedback, what you think about these lectures. You like them, you don't like them, you find them deficient, you find them good. Whatever you find about them, I'll be more than happy to. I'll add on uh, at the end based on what you like and what you don't like, because the idea of this course is that you should understand things very well. And there are courses where the deterministic part is taught very well, and the professor is not familiar with the stochastic part, or the stochastic part is taught in the deterministic. So this is a kind of a unified picture, and that's the idea of this course. Okay, so now let's come to a very widely used term called random processes. Now, what are random processes? Now, another word used for random processes are stochastic processes. Now, this term is very popular among electrical engineers I've seen, and they always are very, inquisitive that how do non-electrical engineers deal with stochastic processes. Well, they use it a lot for signal processing, telecommunications. Now, in the stock market, it's used for financial systems to understand the fluctuations of the price of a stock and to predict the price of commodities based on historical data. Based on the data of today and the past week or the past month, you see a trend and you predict on the future. Now we are going to use it for particle transport because this is what our interest is, that how do particles interact with matter and how can we model that interaction and movement, because we want to carry out a simulation. We do not want to restrict ourselves to regular geometry as you saw for diffusion theory and transport theory. We want to be able to simulate every situation, every possible situation that we might come across practically. So the first thing that everybody looks at when they talk about random processes is is something which is a little bit abstract, and so I would say that this concept of a random process is an abstraction of events that happen and are observed as a collection of random variables. Now the first was a botanist, Scottish botanist named Robert Brown, and he looked at how suspended particles in a liquid move around. So how do they go around making interactions, changing their position, and so on. So I'll show you a little picture uh, of Brownian motion. Now, Wiener was one of the first people to study Brownian motion, and this is a historic time evolution. So, so let's say that you want to model this Brownian motion, and so so what you want to do, you want to look at particle transport, considered as random events. And as I said before, they're born as source particles, they travel in matter, they collide with host nuclei, they transfer their energy, and they undergo interactions until they die by some capture or leakage process. So they leave the place of interest or they just get absorbed. And these events are considered to be random as they're determined from probabilistic interaction data. So this is what we mean by a random process. Now here's a Wiener process. Now if you see this is time on the x-axis going from 0 to 1 second. And W is a Wiener process. So you see it's like the fluctuation of the price of a stock on any stock exchange. So it goes up and down, and see the minor variations in a day, the price goes up and down. So how would you model such a thing? Now let's say you start at 0, at time equal to 0. So what Wiener said is, let's look at a Markovian process. Now a Markovian process is stochastic in nature. It has a future that depends only on the present state without any dependence on its past history. So in this Wiener process, for example, it's called the standard Wiener continuous process, WT. I wrote it as a fancy W because it's a process, it's a random process. Let's say it begins at 0. It has independent increments in which the future is independent of the past. It has Gaussian increments with mean 0 and variance 1, which is called the standard normal. And I'll look at it at a standard normal in more detail as we go ahead. And in the above, what I've done is I've taken a time step of 1 second, broken it down into 10,000 steps. So let's look at the movement of a suspended particle from now in the next 1 second, and let's break it down into 10,000 steps. So what Wiener did was that he said, let's start from W0 is 0, and let's model the time progression WT as, so the next step is going to be this step plus a random number, which is drawn from a PDF multiplied by the delta of the time step. Now, this is independently drawn from a parent PDF, such as a normal distribution. So actually, these are very independent events. So it's identical, it's independent, it's a random variable drawn independently from a normal distribution. Now, several other people, such as Levi and others, have looked at variations of the Wiener process, and many characterizations have been made for modeling the Brownian motion. Brownian motion is so typical of the fluctuations that take place in several situations. So, so that is why it is characterized as sometimes as a stochastic differential equation. Now, when you write it as a stochastic differential equation, you can see that we can put a little drift term over here also. So now this is a stochastic differential equation. Now in the past, I have shown you an ordinary differential equation and a partial differential equation. So this is a whole new area called stochastic differential equations. So here the variables are uncertain. So let's look at this as a fancy x. So dxt is a tx evolves with time dt plus a Wiener process. Now this is what I meant by a random process, a stochastic process. Okay, so this is how people have been trying to understand what happens, and this is exactly what we're going to use in Monte Carlo simulation. So we will, in the stochastic sense, we will say that a history does not repeat itself and a random walk has a probability of occurrence. So in this description of particle transport, nature is understood to behave in a stochastic rather than in a deterministic manner. For those of you interested in a little bit of philosophy, so this was an interesting debate between people like Einstein and Dirac when quantum physics was born, in the process where they used the Heisenberg uncertainty principle, that do you precisely know where an electron is, or does nature sometimes behave in a stochastic manner? So this is called the dual nature of behavior. Even light, Newton said it's particles, Huygens said it's a wave. So there is a picture of atomic behavior which is deterministic, and there's a picture which is stochastic. And it's not correct to say that the stochastic picture is wrong, because there are many events which have shown that the stochastic picture holds. So please do look at this debate in the 1930s, in which Einstein and Planck and Dirac were engaged. Okay, so some terminology: population and sample. Now I told you that a population is something huge, like imagine Avogadro's number. it's 10 to the 23. Now, there's no way that me and you could simulate 10 to the 23 events. So what we can do is that we take a small sample, typically of 1,000,000 neutrons, and we say that this is the sample which we are going to simulate on our laptop, and we are going to infer on what the behavior of the system is for a very, very large number, for a realistic number of events that are taking place. Now, in my experience, what I've done is that whenever I've carried out neutron simulations, Monte Carlo simulations, neutrons and gammas, then I found 10 to the 6 as reasonably good. I've never had to go to 10 to the 7 or 10 to the 8. So 10 to the 6 and maybe a few hours of simulation time are very good. Now, unless you come to very special problems, which we'll see at the end of this course, like shielding. A good shield is something which does not let particles go through it. So if you're simulating 1,000,000 neutrons and only 3 go through it, which they should, then how do you get good statistics in the shield? So shielding is a very challenging uh, problem for stochastic simulation. And so we're going to use techniques when we come there, and I'm going to show you how we can carry out non-analog simulation. So we're going to do some artificial biasing. So let's look at something called a random variable. So let's say you want the age of students in a university. Now, age could be a random variable x, but every student has a different age. So the variable age can take on a continuous set of realizations. Everybody is at a different age. But I can use one variable x to call this the age of students in a university. So when I use the variable x for the age of students, I say that x is a random variable. So it depends on which student I pick. He or she is going to have a certain age. If I pick another student, they're going to have some other age. So x can take the value 21, 22, 24, 21 and 3 months and 6 days. So it can take on different values. So we say it takes on a continuous set of realizations. It can realize a value. So a variable can realize a value. So the probability distribution function is what we need. So if there are 1,000 students and 200 are 21 years old, then you say the probability of finding a student who's 21 years is 0.2. So we can have a discrete PDF, you can have a continuous PDF, but a PDF represents small f of x, which is a density function, which means it's per the thing that you're trying to measure. And it represents the probability that the random variable takes on a realization small x. So here's the integral f of x dx. So between all, if you integrate it between all permissible values, it's got to add up to 100% or 1. And just as I said before, if a PDF does not integrate to 1, or if it does not add to 1, then you're doing something wrong. You're not counting some possible events. So now, what is the probability that the random variable has a value that lies between A and B? So if I integrate the PDF between A and B, I get a probability P of the random variable having a value between A and B. Now, an associated quantity with the PDF is what we call the cumulative distribution function. Cumulative, the word cumulative means to add, accumulate. So cumulative, now if I were to talk about a cumulative distribution function, I'll say how many students in your university are less than or equal to 22 years. So now that means all the students who are 18 and 19 and 20 and 21. So the lower limit is the lowest permissible limit of the variable, but the highest limit of the integral is the question that I've asked. That how many, that what is the probability of finding the random variable having a value less than or equal to a value of interest small x, so that becomes the upper limit. So the only difference between this and this is the upper limit of this integral. Now t is a dummy variable. I could have put anything instead of t. So what's the difference between 240 and 242? The difference is in the upper limit, because of which that becomes 1, and this does not become 1, it becomes a number less than. Now, if I put x equal to infinity, then of course the value will go up to 1. And if I put something bigger than infinity, like 2 infinity or 3 infinity, it would make no difference. So I would say it's a monotonically increasing function, and it saturates at the value, at the uppermost value, and beyond that, it's always the value 1. So a cumulative PDF cannot decrease. It's got to increase. A monotonically increasing function, it's got to increase. Now, the definitions that I've given to you above hold equally for discrete and continuous. So if a random variable x can take on a discrete set of m realizations, where m is 5, capital M, supposing x can only be 10 cars, 20 cars, 30 cars, 40 cars, or 50 cars, then the PDF f of finding 20 cars has got to be small f of I. And the CDF, capital F of xi, so in other words, I ask you, what is a situation where you have 30 cars or less? So it's this possibility, and this possibility, and this possibility. So, and the normalization is that if I say what is the probability of finding a situation where there are 50 or less cars? Well, it's everything. So the probability is 100% or 1 that you find a situation where you have less than or equal to 50 cars. So it's a probability that x has the value xi, and so the p is f evaluated at I, and the CDF is the sum of all the fi's starting from the lowest value to some upper value of interest. An elementary discrete PDF is the uniformly distributed integer between 1 and n, obtained from 1 plus the floor function of n rand. Now, some widely used continuous PDFs, which we use quite a bit, are the uniform PDF, the exponential PDF, the binomial PDF, the Poisson distribution PDF, and of course, the normal PDF. So consider the uniform PDF. Okay, let's start. This is the best, I think, way to teach is that let's start with the uniform PDF. So let's say that everything is equally important. All the students, whether they're 20 years old or 22 years old or 24 years old, so there's an equal number of all students. So let's say everybody is of equal importance, and it's a uniform PDF. So let's first start by a uniform PDF. The other picture I'm going to show you is of an exponential PDF. So let's look at figure 2.5. Now in figure 2.5, what you see is on the x-axis I've written x, which is the value going from 0 to 1. And on the y-axis I've written small f of x. In other words, the PDF. In this picture I've got the same x as above on the x-axis, but on the y-axis I've got the CDF, which is capital F of x. Now notice that if I ask you what is the importance of 0.2, you'll say the importance of 0.2 is this much. What's the importance of 0.4? It's this much. What's the importance of this? It's this much. Now, of course, it's this multiplied by the interval that you're looking at, multiplied by the dx. So that is why the area under this curve, area under this thick line has got to be 1. So this is a rectangle, right? So it's got a length of 1 and it's got a height of 1. So it's a square. And all the numbers are equally equiprobable. If I integrate the function 1 dx between 0 and x, I get a straight line. So I get capital F. The equation of capital F is x. So it's a straight line that goes from 0, 0 to 1, 0. So this angle should be 45 degrees because the tan of this angle should be 1. Okay. So when I come to this later on, that if you're given a CDF, how would you sample X from there? So the way you'd find X is to invert F. So you'd invert F, you know the CDF, so you draw a straight line over here and come down to pick X over here. So that's called sampling, which we're just going to come to. Right now, what I want you to understand is a PDF and a CDF. So looking at this, if I ask you a question, that what is the probability of finding a number less than or equal to 0.8? And you can just go up 0.8, go across over here, and you say it's 80%. What's the probability of finding a number less than or equal to 1? It's 100%. What's the probability of finding a number less than or equal to 2? Now, if you look here, there's no 2 on the x-axis. But since 2 is somewhere over here, so the probability of finding a number less than or equal to 2 would also be 1. So this would carry on and go on as a straight line. Now, this is a monotonically increasing function. Can you see it's not dipping anywhere? It's not going down. So a very important concept here, that this is a PDF written as small f of x. This is a CDF, a cumulative distribution function, written as a big F of x. Now, let me show you the same thing for a CDF. Let me show you the same thing for an exponentially distributed random number. So here are two pictures. There's the PDF and there's a CDF. Now look carefully at this picture. Now what does this picture show you? It shows you that x going between 0 and infinity. I've just shown you a picture going between 0 and 3 because the numbers drop down and there's no point showing you something beyond 3 because it would be the same thing. It's asymptotically coming down to 0. So what you see over here, now qualitatively what you see is that the small numbers are more important than the big numbers. So if this is a situation of interest, then I could easily ignore values higher than 2. I'd say that these are not really important things. So these are the important things. And I'd say these are the very important things. So they kind of tell you the importance of some value of a random variable. Now, this could be if you had some other numbers here, if you had the numbers 2, 3, 4, 5, 6, 7, then this would be the children in a nursery going up to class 1 in school. So the children would be very small, and these children would be less than one year old, and they would be in the play group. So here the children are very important. So there's no older student over here. So if you integrate e to the minus x, so this PDF, the exponential PDF, looks like small f of x is 2e to the minus 2x. Now, what you should do at once is, with a paper and pencil in your hand, you should try to integrate this function f of x going between 0 and infinity, and you should tell me that it integrates to the value 1. And that's what this normalization factor 2 is doing. If I did not have the, what I used to do when I used to teach this course in a quiz, I used to not give them a number over here. And I'd say I've given you a PDF, and what's wrong about it? So basically what I wanted students to do was to integrate this and to show it's equal to 1. So they were supposed to put a constant here, and they had to find the value of that constant. So that's the first thing you teach when you're teaching PDF, that it integrates to 1. So it looks like a e to the minus 2x. And at the value x equal to 0, it should have the value 2, which it does. So when you integrate it, it plots like this. Again, you can see the same features that you saw here. It's monotonically increasing. There's no dip. It goes up and up and up and up, and its slope becomes less and less and less. And here its slope becomes 0, and it levels off to the value 1 and goes on and on and on. So if I ask you, well, of course, it goes on asymptotically, so it never goes to the value 1. So if I ask you what's the, what's the cumulative distribution for x equal to 6,500? So you'd say it's almost 1. Okay. Now let's look how MATLAB can teach us these things very fast. So you go to a graphical user interface. So you give the command distribution tool, this tool, and you can plot so many uh, PDFs and CDFs on MATLAB. So I have a very old version of MATLAB, but I think now I've updated it. But these figures were plotted on the 2009 MATLAB. And I used the random number 2 for randomly sampling from these distribution functions. So there are over 20 distribution functions available. The ones used in this book, in my book, will be mainly the uniform, the exponential, and the normal PDFs. Now you can give the command yourself by saying that x goes from 0. These commands which I showed you, you can reproduce them by saying that x goes between 0 and 3 in increments of 0.1, and y is the function x PDF, variable x, with increments of with the normalization factor, inverse of the normalization factor as half. You can plot it. You can get the sum. You can get the mean value, and so the mean value of the variable x you can get as x1 x f of x dx integrated from 0 to infinity divided by the integral of f of x dx between 0 and infinity. So let me show you that over here. The exponential PDF y is f of x for a given mean mu, and this is 1 over mu e to the minus x over mu. So if mu is a half, the distribution whose mean is a half, so this would be e to the minus 2x, and this would be the number 2. So it would become 2 e to the minus 2x. It would have a mean of half. So that's what is shown in figure 210 over here. Sorry, 210 must be ahead. Anyway, that's what is shown over here. Okay, so let me try to use the program to compute the mean. Now, I've told you that the correct answer is 0.5. So let's look at the computed mean obtained from this expression, what I told you, because that's the definition of the mean value of the variable x, of the random variable x. It is x, the PDF, f of x dx, integrated over 0 to infinity, divided by this normalization. So if x is 0, if a is 0 and b is infinity, then this becomes 1. But any other integral you can calculate like this. And so what I did was that uh, for a pretty bad big interval between 0 and 3 of 0.1, I got not such a good answer. I said that the mean value, the computed mean, comes out to be 0.4454. Now, if I improve that by going from 0.1 to 0.01, so I take 100 more values, I get 0.4877, 0.001, 0.4921, 0.0001. So you see that I'm coming to 2.5. Okay, so now let's say you've got two discrete random variables. So you've got joint distribution functions. So the case that I just showed you was for one variable. Now supposing, so I put a little example over here, that supposing you've got two random variables, x and y, with realizations small x, small y. And supposing you've got n sets of these, so x1, y1, x2, y2, x3, y3, all the way up to x100, y100. So supposing n is 100, and I say that each of those sets has a probability 1 over 100, so each one is equally important. It's equiprobable. So let's take as an example. Then I want to show you what I mean by the terms mean, variance, covariance, and correlation. Now the mean, as I told you in the continuous case, was the integral of x, the PDF, f of x dx integrated over dx. For the discrete variable, the definition would be that the expectation value of the variable x, written like this, would be the sum of the value of x multiplied by the probability of occurrence of that value. The same thing holds for the random variable y, so this would be its expectation value. Now notice over here that up there I gave you the joint PDF, but here I'm not using the joint PDF, so I'm using the single PDF. So I've got to define the single PDF for the single variable. So for x, I'd have to integrate them over all y's, and for y, I would have to integrate them over all x's. Now, variance. Variance means how much does anything vary from the central tendency of that variable. So the variance for x is the formula which I should have derived here, but it's trivial actually. It's just the integral of x minus x bar whole square, f of x dx. And it comes out to be the expectation value of x squared minus the expectation value of x whole square. I'm going to be using this a lot. I'll show you MATLAB programs where it's used a lot. Now, similarly, we define the covariance of two variables, x and y, as the expectation value of the product of these variables minus, so this e should have been up, so it's a misprint over here, minus the products of the expectation values of x and y. Then we have a correlation coefficient between the two variables, and this is something you must have heard so much about. So the correlation between two variables is the covariance divided by the square root of the product of the variances of x and y. So I'm sorry, this should be fy and y, and this should be x. So let's look at this page again. If you look at this page again, so the expectation value of both variables, the definition of the single PDF given a joint PDF, given capital N sets of pairs, the variance, the covariance, and the correlation. Okay, now I thought I'll put in some numbers to take you through an exercise so that we can get a good picture of things. Now, the correlation coefficient lies between -1 and 1. So if you say the correlation between two variables is -1, that means what are the chances that it's going to rain tomorrow and that I'm going to have a chicken burger. So there's absolutely no correlation between the two. So then I'd say that if x represents my probability of having a chicken burger and y represents the probability of it raining tomorrow, so they're completely uncorrelated events. But if I ask you the question that there's a man driving in a Rolls Royce, and so X represents how much money he's got in the bank, Y represents the car that he's driving. So is there any correlation between the two? Well, yes, would say a rich man would be driving a Rolls Royce. So there the correlation would be 1. You would not see, the opposite of that. So similarly, the price of oil, the price of gold. So these days, coronavirus, the price of oil has gone down because there are much fewer buyers. So it was correlated with events in the world. So the price of stocks is correlated with the political stability, with the environment, etc., etc. So finance people really like this coefficient, and so do we, because we want to see whether two variables are correlated or whether they have nothing to do with each other. So are they uncorrelated or are they fully correlated? Okay, so let's look at this example over here. So let me give you 1, 2, 3, 4, 5, 6 sets of x, y values. And let me say that none is more important than the other. So each one has a probability of occurrence of 1 over 6. So let me make f of x for x. Let me integrate it over the y's. So how many x's do you see? You see a 0, 1, 0, and 1, 1, and 2 minus 1s, and 1, 2. So the minus 1 is all alone. Sorry, the minus 1, there are 2 minus 1s, is here and here. So there are 2 times 1 over 6. So the probability of finding a minus 1 is 2 over 6. Similarly, the probability of finding a 0 or a 1 can happen twice out of these 6 numbers, 6 sets. So I'd say, sorry, the probability of 0 happening is 1, and the probability of finding a 0 is 1 over 6, and the probability of finding a 1 is also 1 over 6 because there's just one of each. So it's 1 over 6. The probability of finding a 2, now there's no 2 in the x over here, there's none over here, there's none over here. So there's 1 over here and 1, so there are 2 2's. So actually, I could have written a minus 1 comma 2 over here, so I didn't realize it at that stage. Okay. Now let me try to find the expectation value of x. So here's the variable x. So x can take on the value minus 1, 0, plus 1, plus 2. These are the probabilities. So minus 1 you'd find with a probability of 2 over 6. 0 you'd find with a probability of 1 over 6. 1 you'd find with a probability of 1 over 6. And 2 you'd find with a probability of 2 over 6. So I find the expectation value of x as 3 over 6 or a half. Now I find the expectation value of x squared in the same way. I squared this number, I squared this number, I squared this number, I squared this number, and I multiply them by the individual probabilities, and I get this number. From this number, I get the variance, the spread of the random variable x as the expectation value of x squared minus the expectation value square of this, and so that comes out to be 1.5833. So you see now this is for x, and I'll have to repeat that for y. So let's do the 3 things for y again, so you can see exactly the same thing that they've done for y. I get the expectation value of y, I get the expectation value of y squared, I get the variance of y, then I get the covariance expectation, then I multiply the x by the y, the x by the y of the first set, the second set, the third set, the fourth set, the fifth set, and the sixth set. So when I do that, so I get 2 over 6 as a covariance. Now let me find the correlation between the two variables using this formula. Again, this is x, this is y. So if I put in the covariance, I put in the variance of x, the variance of y, take the square root, then I find that the correlation is 0.2. So yes, they are correlated. They do have an influence on each other, but not a huge dependence on each other. Now, a huge dependence would be like, imagine a linear curve, that if one increases, the other increases. So this is saying that there's a 0.2 correlation. So it's not 100%. Okay, so I think I'll stop over here. And in the next lecture, I'll come to random numbers.